Alright guys, so welcome to another lecture, right? So we move on to the Trigonometric Functions chapter, right? So this is section 12.2 on Trigonometric Functions and their graphs. Right, so what are we going to do here? We are going to introduce the trigonometric ratios, look at special triangles and special values of trigonometric functions related to different ways, right? So the unit circle tables are right triangles. And finally, we are going to have some fun and play with trigonometric identities, okay? First of all, let's define the trigonometric ratios, right? You might have heard of them, okay? So, but where are they coming from? Well, first of all, you might want to consider a right triangle, right, with theta as one of its acute angles, right? So keep in mind that for a right triangle like the one we have in the picture, here we have the right angle, right, which is a 90-degree angle, and on the other two angles, one of them is acute, the other one is acute as well, right, which is denoted here, right? So when we want to find the trigonometric ratios, we need to be sure about the reference angle, right? We cannot just put the angle theta on one side or the other. No, we need to fix the position of the angle, because that's going to be the starting point for determining which angle will be the opposite, which one the adjacent, and which one, and then the hypotenuse, all right? Okay, so the two sides, the adjacent and the opposite, are going to be the ones that form the 90-degree angle, while the diagonal will always be the hypotenuse. Okay, so if this is our reference angle, right, theta. Okay, notice this side, which is the vertical one, is facing in the opposite direction as the angle, right? And let's highlight that one with purple right here, while the adjacent means close to, right? Close to the angle, right? So notice how this side is adjacent, right? Because it's close, not opposite, not facing on the opposite side of the angle, right? And this is how we define the trigonometric functions, right? Let's start with the first one, okay? Sine, which is opposite over, let me use a different color here. Okay, opposite over hypotenuse. All right. On the other hand, cosine is adjacent over hypotenuse. Okay. Tangent will be defined as the opposite side over the adjacent side, and the other three functions they are actually the inverses of the other ones, right? Let's see how that works. So actually, let me change color here. Adjacent, in this case, it's going to be, we are going to have cotangent theta adjacent over opposite. All right, and let me use the hypotenuse as, let me change color to purple for, never mind. So secant and cosecant, for secant hypotenuse over adjacent, right? And you can see how secant is really the inverse or the reciprocal of cosine, right? Secant is hypotenuse over adjacent, and cosine is the reciprocal, which is adjacent over hypotenuse, right? We're gonna look at this later when we work with trigonometric identities, right? Now, given a triangle, right, of side of we're gonna give the lengths of the sides of a triangle. we are going to be very often we are going to be asked to find the 6 trigonometric ratios of the angle theta, right? Let's look at one example here. So we are given a right triangle in which the hypotenuse is 5 and the opposite. Notice this is the opposite because this 3 is facing in the opposite direction against, if you will, the angle theta, right? So they're asking us to find the 6 trigonometric ratios. However, we seem to be missing one piece of information. We don't know what the adjacent side, the length of the adjacent side is, right? So in this case, we need to figure that out here, right? So notice we have a right triangle and we are given two of the sides, one of the sides and the hypotenuse, right? So we can use one theorem that relates the three sides of a right triangle, in this case the Pythagorean theorem, right? That says a squared plus b squared equals c squared, right? We don't know what a is, right? That's what we're looking for. You can think of b being 3 and the hypotenuse is always c, right? So a squared plus b squared, which is 3 squared, equals c squared, which is 5 squared. So a squared, let's simplify this. So that's going to be 9 equals 25. Okay, and then let's isolate. Okay, let's be careful here. Don't want to confuse the 9 with the a. They look sometimes when I write a's with 9s, they look the same. Okay, so a squared equals, subtract 9 from both sides, we get 16, and take the square root on both sides, we get a equals, we should get plus or minus the square root of 16, which is plus or minus 4, right? However, in this case, we're looking at a length of one of the sides of a right triangle, so we don't need to use this plus or minus, right? So there's no way that it wouldn't make sense to have a negative side, right? So let's just keep the positive angle, right? The positive length, rather. All right, now that we have the three, right? We have the three pieces of information. We are ready to evaluate the 6 trigonometric functions. Let's begin with sine. Sine theta, sine of the angle, which will be 3/5 because this is the opposite and this is the hypotenuse, right? The definition of sine is opposite over hypotenuse, that is 3 divided by 5. Okay, let's look at the second function, cosine. Cosine theta equals, by definition, this will be adjacent divided by the hypotenuse, right? In this case, 4/5. Let's write down the definition. Adjacent over hypotenuse, right? And then let's go with the next one, tangent, which is by definition the ratio of the opposite to the adjacent, in this case 3/4. All right, so this is opposite over adjacent, and we have 3 more. Okay, for cotangent, this will be the reciprocal of tangent, right? In this case, this is adjacent over opposite, right? In this case, adjacent over opposite, which is 4/3. That is the same as the reciprocal of tangent, right? That is 4/3. And let's write the definition, right? Adjacent divided by opposite. 2 more to go, all right? Secant theta equals, well, notice how secant is the reciprocal of cosine, right? So we used to have adjacent over hypotenuse. So we are going to have hypotenuse over adjacent. Okay, in this case, hypotenuse, which is 5 over adjacent, so 5/4. And finally, cosecant theta, which will be the reciprocal of sine, which in this case, sine again was opposite over hypotenuse. So cosecant will be hypotenuse over opposite. In this case, 5, which is the hypotenuse, 3 over the which is the opposite. Okay, so now let's write that as a ratio 5/3. All right, and this is one example right, to find the trigonometric ratios of a given right triangle and the lengths of its sides. All right, let's see. Let's do another example, a very similar example, right? So let's see, we are given one of the sides and the hypotenuse. However, you need to be very, very careful every time you have a problem like this, right? You need to be careful about the reference angle, right? This is the reference angle right here, this corner right here, given by that symbol theta, right? And the opposite will be 7, right? However, we need to find the adjacent. So we know, again, by the Pythagorean theorem, a squared plus b squared equals c squared, all right? That's what we know from Pythagorean theorem. Let's use it again. We have a this time, right, which is 7. It doesn't matter because ultimately it's a sum, right? I'm just going to go with the order, all right? So, and b squared equals c squared, which is 8 squared. 7 squared, which is 49, plus b squared equals 8 squared, which is 64. If we subtract 49 from 64, we should get 15. And b will be, again, take the square root, 15. Again, no need to put the plus or minus because, again, the lengths are supposed to be positive, okay? So let's write down our ratios now, right? So sine theta, which will be opposite. Okay, be careful here because notice how the triangle is rotated and the acute angle as a reference is different, right? So in this case, the opposite, let me highlight it as I go. Opposite over hypotenuse, that is 7/8. Okay, 7/8. All right, and there's nothing to do here. Then cosine, which is cosine theta, which is the adjacent, right? This is the adjacent over the hypotenuse. The adjacent square root of 15 over 8. And then the tangent function, tangent theta, will be the ratio of the opposite over the adjacent, right? In this case, 7 divided by the square root of 15, all right? However, be careful here because you may not want to leave radicals in the denominator, so you might want to rationalize these denominators by multiplying and dividing by the square root of the number in the denominator. When we multiply square root of a number times itself, the square root cancels. We can just simply cancel 7 root of 15 and simply 15. How come this is possible? Okay, let me do it on the side. Okay, when you multiply, hold on, something happened. Okay, there you go. When we multiply square root of 15 times square root of 15 itself, right? Think of having 15 to the 1/2 and times itself 15 to the 1/2. In this case, notice we have the same base multiplying, that is 15. By the rules of exponents, we add 1/2 plus 1/2, which ultimately adds to 15 to the first power, which is just 15, right? So that's why we can just cancel, write down the number inside and cancel. Another way to see this is, okay, let me write it down here. 15, the square root of 15 times itself is the same as saying the square root of 15 quantity squared, in which the power 2 cancels the radical symbol, right? And that equals 15, okay? That's another way. Okay, so that's just a mini review of what you might have learned in your Math 96 or any other intermediate algebra course, right? Okay, let's keep moving on with the other trigonometric functions. That's cotangent theta, which in this case is adjacent over opposite, which is the reciprocal of tangent. All right, in this case, the square root of 15 divided by 7. The function secant theta, which is hypotenuse over adjacent. All right, hypotenuse over adjacent, which is the opposite, or rather the reciprocal, not the opposite, the reciprocal of the cosine function, a divided by the square root of 15. All right. However, again, in this case, just like the previous couple of examples, you might want to rationalize denominators. Root of 15, all right, and a root of 15 divided by 15. And finally, and not but not least, cosecant theta, which is defined as hypotenuse over opposite, which is the reciprocal of the sine function that I'm highlighting, right? So all we do is simply invert the sine function, okay? How can this problem be worded differently, okay? So in this case, we're going to be given a piece of information, right? Cosine alpha equals 3/4, right? That's all the information they're giving us. Now they're asking us to sketch a right triangle with an acute angle alpha and then find the other 5 ratios of alpha. Okay, let's see. So notice in this case we're not using thetas. However, they're using alpha. So typically, let's go over this very quickly. The letters for angles. Typically, we use lowercase alpha, beta, maybe sometimes gamma. No, not delta. I believe we use theta, phi, which is similar to theta, and then what else? Is there another symbol for angles? I believe psi. I believe that's another very common letter for angle, right? So those are the most common Greek letters used for angles, right? So, okay, let's see if I can use a shape to draw a triangle here. Okay, I do a triangle, but I need a right triangle. This, oh, I think this does right triangles, but not quite. You know what? Never mind. I'm just gonna do it by hand. Okay, so I'm gonna draw a right triangle. All right, and this is the angle alpha. And they're giving us cosine, right? Okay, so eventually we will find sine of alpha. We have cosine of alpha, right? We don't know what sine is yet, right? But we're going to figure that out. So this is cosine alpha, that's 3/4. But what is the definition of cosine? Again, this is adjacent and this is hypotenuse. All right? So let's put letters to this. The adjacent, again, this is not the adjacent. Again, the one that I just labeled is the opposite. Notice how it's facing against the angle of reference angle alpha, right? So the correct labeling would be this, right? So we need to find the vertical side. Again, what are we going to do? We are going to use our Pythagorean theorem, right? So a squared plus b squared equals c squared. So a squared, which is 3 squared, plus b squared, which we don't know, right, equals 4 squared. That's going to be 9 plus b squared equals 16. Subtract 9 from both sides, we get 16 minus 9, that's a 7, and b will be the square root of 7. Okay, so again, yes, it looks like we're going to do more rationalizing the denominators, but now that we have the 3 pieces of information, we're ready to define the rest of the trigonometric functions as requested, right? So the ratio sign is going to be the opposite, which I'm highlighting, over the hypotenuse. Okay, that's square root of 7 divided by 4. Tangent alpha, which is opposite over adjacent. All right, so this will be opposite over adjacent. Cotangent is no other than is related no other than the reciprocal of tangent, right? That is 3 divided by the root of 7, right? By definition is adjacent over opposite. However, no radicals in the denominator, so let's rationalize the denominator. Okay, we're going to get the following. 3 root of 7 in the numerator by just multiplying across and multiplying the root of 7 times itself. Get rid of the radical symbol, just write down the radicand. That is the quantity inside the radical. The next trigonometric function, secant alpha, which is no other than the reciprocal of cosine, 4/3. And last but not least, cosecant alpha, which is no other than the reciprocal of sine, which is 4 over root of 7. But again, you might want to rationalize this square root of 7 in the denominator, right? Okay, so let's root of 7, root of 7. Okay, this will give us, by multiplying across 4 root of 7, divide by 7. And there we go, the 6 trigonometric functions, right? The 6 trigonometric ratios. Now that we are familiar with the different ratios, right? So you might want, let's look at evaluating trigonometric functions with using different methods. And by the way, we are going to look at special triangles. So of course, we are going to, in real life, we may deal with triangles, right? Triangles that may have random angles, right? However, for at least for a calculus class, in general, mostly we are going to work with special angles, and those special angles are 30 degrees, 45 degrees, and 60 degrees, and their multiples. We're going to look at something called trigonometric functions and their periodicity and how to find those values, right? So let's move on to the next topic. All right, so we're going to work with evaluating trigonometric functions using one method. The one method using special triangles, and we are going to look at 2 special triangles here. Those 2 special triangles are going to be, number 1, the 40, 90. Okay, let me find a good highlighter here. Okay, so the 40, 90 degree, 45, 45 rather, 90 degree, and the 30, 60, 90 degree triangle, right? Again, keep in mind that if you add these 3 angles, you will get an 180 degrees. And the fact from geometry, right, is that the addition of the inner angles of a triangle is 180 degrees. If you add also 30 plus 60, that's going to be 90 plus 90, same, 180. Okay, so let's see, how are we going to derive the special values for the 45, 45, 90 degree angle. All right. Okay, consider the unit square. All right, the unit square is a square of, that's just a fancy name for a square of side 1, right? Okay, so let's write it down again. Unit square. That's what it is. Okay, so notice the length is 1 and the height is 1, right? If we find the length of the diagonal, which is marked in red right here, the one that I'm highlighting, well, let me use an actual highlighter so we can see it. This one right here, the one I'm highlighting, well, in that case, we would get the square root of 2. Let's do that on the side real quick. You might want to use the back side of your page or the space below if you're writing all this down, right? So a squared plus, okay, a squared plus b squared equals c squared. So 1 squared plus 1 squared equals c squared. So that's going to be 1 plus 1 equals c squared. And that's 2 equals c squared. Take the square root on both sides is the square root of 2, right? Which is what they have here. Okay. And those are going to be the values related, right, to the triangle, the special triangle that has angles 45, 45, 90, or if you prefer, well, not that you prefer, I mean, we need to get used to the radian measures, right? Because we will be working a lot with radians, right? So don't get too attached to, let's not get too attached to degrees because we may not use them very often, right? So what about the other triangle? Okay, so now let's consider an equilateral triangle, right? An equilateral triangle ABC, right, of side 2 each of them, right? And then let's draw a perpendicular bisector denoted dB of the base. Okay, a lot of words, a lot of letters. Let's do one thing at a time. All right, so we're going to consider a second triangle. The second triangle is the one we have on the left right here. Notice the length of each side that I'm highlighting is 2 units, 2 units, and 2 units, right? It's an equilateral. That means equal sides. Equilateral means equal side. The length of each of all sides are the same. Okay, what about this perpendicular bisector? So from one of the corners, it doesn't matter. You could have done the bisector in this direction, right? And get it like this, or get it like that, right? But for visual reason, this picture which is really nice, by the way, does it vertically and changes the colors for red and blue for the two triangles now. So that means this bisector is turning an equilateral triangle into 2 right triangles, right? We are going to use only one for reference, right? So let me go to the side right here again, right? So let me reproduce this picture. So, oh, good thing we have I can do an equilateral triangle using this, right? Remember, that's what I tried to do. Whoops. Okay, I need this and the shapes. All right. Okay, so that looks like an equilateral triangle. Okay, let's see. And the bisector right here. So basically, I'm just animating the movie that we were looking before, right, about the triangles. Okay, and then this will be the shapes. And let me move it a little bit. Having a hard time to move this one to get the bisector. Okay, it's not easy. Never mind. Okay, let me do it by hand. And this right here, right? So I'm going to highlight this right? The length is 2, the length of the side is 2, the length of the side is 2. If I choose only this triangle, half of it, okay, let me do it here. Okay, no, this is 2. Like this, all right? Okay. What about the angles in the third, in this equilateral triangle? Okay, the angle, it would be a good idea to label. This is 60 degree. This is also 60 degrees, right? And this is also 60 degrees. If you add them, you add the 3, 60 plus 60, that's 120 plus 60, that's 180, right? But now, when I apply this bisector, or this perpendicular bisector, okay, this remains 60 degrees. This is a 90 degree, and this 60 degrees, because it's being bisected, I mean, it's cut in half. This is a 30 degree angle, right? And let's add the angles. 30 plus 60, that's 90, plus 90, that's 180. Okay, let's at the same time, this is still 2, right? That is still 2, the diagonal. And well, when we draw this bisector, right, to take half of the triangle, right, this 2 gets cut in half. Half of 2 is 1. So we need to figure out the length of the vertical side, right? So to do that, we use the Pythagorean theorem. Okay, so a squared plus b squared equals c squared. So we know that a squared is 1 squared plus b squared, which we don't know, that's to find out, and then c squared equals 2 squared. So that's 1 plus b squared equals 4. Okay, and then let's subtract 1 from both sides to get 3, and b equals the square root of 3. Again, no need to put the plus or minus coming from the square root property, right? Because we are looking at a length of a triangle, right? And it doesn't make sense to use the negative sign. Now that we know this length, which is square root of 3, let's go back to the picture that you have. Isn't that the same, right? Okay, let's highlight 1, 2, root of 3. Okay, and in this case, we may now use those triangles, right? Now we're going to use these triangles, special triangles, right? Omit the 5 and 6 that was taken from the textbook. They were not labeled actually. And now we can find the trigonometric ratios for those special angles, right? The angles that we will be working most likely for the rest of the chapter, okay? All right, evaluate the 6 trigonometric functions for theta equals pi over 6, okay? Pi over 6, what is pi over 6? Okay, how about, let me relabel this, okay? Okay, so let me highlight 30 degrees is pi over 6, right? We already looked at this on the previous section, right? Going back and forth between degrees and radians and degrees. And then the 45 degree will be pi over 4, and 60 degrees pi over 3. Okay, so what are we going to do? We are going to find the trigonometric functions for pi over 6, which is the same as 30 degrees. All right, in order to do this, okay, let me use a shape. Okay, let me see if this works. Okay, this should be enough space, hopefully. Okay. All right. And this is what we do. We're going to draw a triangle, right? I'm going to use blue. And this will be this angle, a 30-degree angle, right? What are the sides? The sides, okay, let's go up to the picture right here. Notice the 30-degree is smaller than the 30-degree right here that I'm circling is a smaller angle than 60 is, right? So in this case, look at the orientation of the triangle. This will be 1, 2, and root of 3. Okay, that's enough information, right, to find the ratios of the 6 trigonometric functions. So sine of pi over 6 will be opposite over hypotenuse, which is 1/2, right? Again, highlight the opposite, highlight the hypotenuse, right? Cosine pi over 6 equals square root of 3 over 2. Okay, there goes the first couple ones. Okay. Tangent of pi over 6. That will be, by definition of tangent, that's opposite over adjacent. Okay, which in this case is 1 over the square root of 3. And again, you might want to rationalize the denominator because you may not want to end up with radicals in the denominator. So this will be root of 3 over 3. Again, multiply root of 3 by itself, we get just the number 3. Let's write down the other 3. So cotangent, so by now we should keep in mind, right? We should be aware that cotangent is no other than the reciprocal of tangent, right? Root of 3 over 1, which is simply root of 3. Secant pi over 6, which is the reciprocal of cosine, or hypotenuse over adjacent, which is 2 over root of 3. And again, you might want to rationalize this one to get simply 2 root of 3 divided by simply 3, all right? And cosecant pi over 6, which is 2 divided by 1, which is simply 2, right? And there we go. There we go, those the first example. Now let's evaluate the 6 trigonometric functions for pi over 4, which is, by the way, 45 degrees. Okay, all right. Let's draw another Cartesian plane, okay, in which the triangle will be the 45 degrees, right? Which we know the sides are 1, 1, and square root of 2, right? And let's go back and recall the picture, see? Okay, let me erase the circles here. So the sides for a 45, 45, 90 degree are 1, 1, and root of 2 for the hypotenuse. That's what we're going to be using for this, right? The same, right? The angle theta is 45 degrees. And let's start by writing sine pi over 4. Sine pi over 4 will be the opposite, right? Opposite over hypotenuse. That is 1 divided by the square root of 2. And you might want to rationalize the denominator to get root of 2 divided by 2. Cosine pi over 4. By definition of cosine, we know cosine is adjacent over hypotenuse. However, you might notice it is the same as sine. I'm not going to do the rationalizing. I'm just going to write it. All right, I'm going to just omit that step. It's the same. I want to repeat myself. Tangent pi over 4. All right. Let's see. That's opposite over adjacent. Right? Opposite over adjacent, that is 1 over 1, which is simply 1. Okay, let's evaluate the other three functions, the other three trigonometric functions. Cotangent. Cotangent of pi over 4 is the reciprocal of tangent, which is adjacent over opposite, which is 1 over 1 again. And 1 over 1 will be 1, just the same way as cosine, right? Secant pi over 4, which is the reciprocal of cosine, or hypotenuse over adjacent, which is simply root of 2 divided by 1, which is root of 2. And cosecant, last but not least, cosecant pi over 4. That is hypotenuse over opposite, which is exactly the same as secant in this case, right? So that's root of 2. I'm just going to write root of 2. Okay, same. Right? Let's do another example. Let's do the pi over 3. The trigonometric functions for pi over 3. All right, so pi over 3, keep in mind this is the 60-degree angle. Okay, let me go back a little bit. Go back to, and we are going to use exactly this triangle in red because our reference angle will be the 60-degree as I just circled, right? So let's just bring it and let's see, let's draw a Cartesian plane first, all right? And let this be black, okay? And this, okay, this may not be perfect, right? I'm trying my best to draw this triangle, right? This is going to be 1, 2, and root of 3. And this will be our reference angle theta, which, by the way, is pi over 3, or 60-degree angle, by the way. And then we go back to do that labeling here. This is pi over 4, or 45. And for the first example, I think I did 30 degrees, or pi over 6, right? Same thing. Okay, let's evaluate the 6 trigonometric functions for the other triangle, 60 degrees. Okay, so let's begin by evaluating sine. Sine pi over 3, which equals sine, by definition, opposite over hypotenuse. Okay, root of 3 divided by 2, cosine pi over 3 equals adjacent over hypotenuse, that's 1/2. Tangent, which is opposite over adjacent, that is root of 3 over 1, which is simply root of 3. And then on the other hand, we're going to evaluate cotangent pi over 3 equals adjacent over opposite. That is 1 divided by root of 3. But what are we going to do here? Rationalize the denominator. Okay, so this is root of 3 over 3. Secant pi over 3 equals the reciprocal of cosine, which, by the way, in this case will be hypotenuse over adjacent. That's the definition of secant. All right, that is 2 divided by 1, which is simply 2. And cosecant, that will be hypotenuse over opposite. Okay, let's write that ratio, 2 divided by root of 3. And by the way, you might want to rationalize this guy. Okay, and this will be 2 root of 3 divided by 3. Okay, so those are the trigonometric values of the three special angles: 30 degrees, 45 degrees, and 60 degrees. All right. Now, notice in this case we will be evaluating trigonometric functions of other angles, right? Like 5 pi over 6. Okay. What is 5 pi over 6? 5 pi over 6, okay, let's change that to multiply by 180, divide by pi. And if I do this, 180 divided by 6, that's 3, that's a 30, and then times 5, 30 times 5, that's 150 degrees, right? Okay, what about it? Why am I doing this? Okay, so let me draw another Cartesian plane here. All right. So in this case, this is what I will do. I'm going to do, this is our initial, that's a 0 degrees, and we are going to move the ray 150 degrees, right? So initially, this is our 150 degree. However, that's not a right angle, right? In fact, that's an obtuse angle. So this is what are we going to do? We are going to form a triangle, in this case, in the second quadrant. Let me go back to the previous examples. Notice I was evaluating pi over 6, right, or 30 degrees in the first quadrant, right? The same way we were evaluating pi over 4 or 45 degrees, likewise in the first quadrant, right? Pi over 3, which is 60 degrees, was also evaluated in the first quadrant. So what happens if we wanted to evaluate trigonometric functions of other angles, like 5 pi over 6, like 7 pi over 4, and yes, we are going to do, but those angles won't lie on the first quadrant. So this is what we will have to do. We are going to draw the diagonal, the terminal side, and then draw a vertical line from the end point of the terminal side, draw a vertical line from there to the x-axis, and form a right triangle there. All right, notice that half a turn, right, from here to here, what I'm doing is 180 degrees, right? The reason why I was finding all the angles in degrees, because on the one hand it will be easier to see the difference between 180 and 150. The difference is no other than 30 degrees, right? So what do we have? We have 30 degrees, or pi over 6, however, on the second quadrant, right? I'm going to use quad 2 to denote second quadrant, right? Okay, let me erase it. I think let me make it easier to read. So that's a second quadrant, right? Okay, so we are going to honor the values for the 30-degree angle, which are going to be 1. The hypotenuse will always be positive. However, Notice the direction of the adjacent side, of the horizontal side. Notice in this case it's going in the negative direction, so that's a negative root of 3. All right. So that's the tricky part about angles that lie other than the first quadrant. We need to be just careful with the sign. So sine theta will be opposite over hypotenuse, that's 1/2. Cosine theta will be adjacent over hypotenuse, right? We are going to be working with these numbers for every single angle. What will most likely be changing is just the sign. You will see the patterns right away. And tangent theta, that's opposite over adjacent, which is going to be, okay, again, be careful to rationalize denominators, negative root of 3 over 3. Now what about the other ones? Cotangent, which is hypotenuse of, no, not hypotenuse, adjacent over opposite, which is the reciprocal of tangent, right? Root of 3, negative root of 3 rather, over 1, which is just negative root of 3. Secant, which will be hypotenuse over adjacent, negative 2 divided by negative root of 3. And rationalizing this denominator, we should get the following: 2 root of 3 divided by 3. And don't forget the negative sign. Okay, this should be a negative number. Okay, and cosecant theta. Well, in this case, I should have written 5 pi over 6 instead of theta, right? I'm just writing theta, it's the same, right? Cosecant, which will be hypotenuse over opposite. That is 2 divided by 1, which is 2. All right. And there we have the 6 trigonometric functions. All right. What about evaluating the 6 trigonometric functions for 5 pi over 4? All right. I'm going to do another Cartesian plane here, right? Cartesian plane, and let's draw 5 pi over 4. So you might want to convert this to degrees to have an idea of how far are we going to go, right? So if we convert, okay, pi's go away. 180 divided by 4, that's 45. 45 times 5, that's 225. All right. So 225. So from 180. Okay, so this is 180 plus 45, right? So this is 180, right, so far. Well, let me leave the 180 for later. Okay, let me do the initial and terminal. All right, so essentially this is our, okay, what's going on here? Is this, no, not linked to shape. Something weird is going on. Okay, never mind. Okay, so this would be the initial and our terminal spanning 225 degrees. But again, that's a really huge angle to be contained inside of a right triangle, right? So that's why we are going to use the related triangle, right? So in this case, How far is 225 from 180? Okay, so just the same way we did it on the previous example, right? This is a 45-degree angle, or pi over 4, in the third quadrant. All right, on the third quadrant. And then because we have the 45-45 triangle, right, the measures of a 45-45 triangle are 1, 1, and root of 2. However, we need to honor the direction of the sides. In this case, notice the horizontal direction is going negative and the vertical direction is going down, which is also negative. The hypotenuse is always positive, all right? So don't, just keep that in mind. And I guess we're ready to find the 6 trigonometric functions for 5 pi over 4. All right. Let's see. So sine 5 pi over 4 equals sine, which is the opposite, over hypotenuse, right? Okay. Keep in mind that this is the reference angle, right? Theta. Theta equals 45, right? So that's going to be negative 1 divided by root of 2, which is negative root of 2 over 2, okay? Right, when after rationalizing. Then cosine, okay, let me actually do the rationalizing steps so you don't freak out so you know where is this coming from. And this will be negative root of 2 divided by 2. Cosine 5 pi over 4, it's going to be the same, negative 1 over root of 2, which is the same as negative root of 2 over 2 from the previous step, right, from sine, because it's the same numbers even though it's adjacent over hypotenuse. Notice it's the same numbers as in the sine function. Cotangent 5 pi over 4 equals, no, not cotangent yet, never mind, moving ahead, it's tangent, not cotangent. Tangent of 5 pi over 4, that's opposite, which is negative 1 over hypotenuse. Let's highlight opposite over adjacent, not hypotenuse, adjacent, opposite over adjacent, which equals, dividing negative 1 by 1, we get positive 1. Okay, cotangent 5 pi over 4 equals the inverse of tangent, but isn't that the same as negative 1 over negative 1, which is the same as positive 1, right? And then secant 5 pi over 4 equals the reciprocal of cosine, right, which I'm highlighting here, that is negative root of 2 divided by negative 1, which is simply negative root of 2. And cosecant of 5 pi over 4 equals square root of 2 as well, divided by negative 1, which is the reciprocal of sine, right? And that's going to give us negative root of 2. And there it is, the 6 trigonometric functions, all right? Okay, let's do one more. Yes, we're spending quite a bit of time on finding trigonometric values, but it is very important to get used to the trigonometric values of special triangles, and especially our focus on examples 7, 8, and the next one 9, which is how to go about angles that do not lie anymore on the first quadrant, right? Like 11 pi over 6. which is, okay, but rather times. Let's change, multiply by 180 and divide by pi. We are going to get 180 divided by 6, so 180 divided by 6 is 30. 30 times 11, that's 100 at 303 and 330 degrees, right? All right. How far does this angle go? Okay, so this angle goes as far as, okay, this is the 0, right? And we are going to rotate counterclockwise all the way to 330 degrees, right? This is 330 degrees. That's a very huge rotation, and the angle that is given, that gives rise to, it's going to be, well, what's the difference between 330 and 360? That's just 30 degrees, right? Okay, so I didn't mean to do that. I just wanted to erase the 30. All right, and the line, oh no, not the line, Control Y. Okay, I just want to erase this right here. So this will be a 30-degree angle, or pi over 6. All right. And the lengths of the sides for 30-degree angle, this is 30, not 36. All right. This will be 2, 1 root of 3. However, okay, notice the square root of 3 keeps the positive sign because extends in the horizontal to the right. However, 1 changes to negative because it's extending vertically down, so we go with the sign. Okay, and this is going to be our theta. Okay, this 330, right? 330 degrees is the same as 30-degree in the 4th quadrant. Just the same way, let me go back to this again. Just the same way, 225 is the same as saying is the same as 45 degrees in 3rd quadrant. On the other hand, the 150, okay, what was 150? It was a 30-degree, is the same as 30 degrees, right? It's the same as 30 degrees in 2nd quadrant, right? So that's how we work on this, right? Okay, so let's look at, let's evaluate the trigonometric function. So sine theta, sine, which is opposite over hypotenuse, right? In this case, -1 divided by 2, which is -1/2. Cosine of the angle theta 11 pi over 6 equals adjacent divided by hypotenuse. Okay, in this case, the square root of 3 divided by 2. Tangent theta equals opposite over adjacent, which is -1 divided by root of 3. But again, you might want to rationalize the denominators. Okay, so this will be negative root of 3 divided by 3. Cotangent theta equals the reciprocal of tangent, which is adjacent over opposite. So this will be root of 3 divided by -1, which is negative root of 3. Let me keep going here. Secant theta. This will be the hypotenuse over adjacent, which is really the reciprocal of cosine. Again, 2 divided by root of 3. And again, you might want to rationalize the denominator here and simplify this. This is 2 root of 3 divided by 3. Cosecant theta equals the reciprocal of sine, right? Sine is by definition opposite over at hypotenuse. So cosecant is hypotenuse over opposite. Okay, so 2 divided by -1, which is -2. And there we go, we evaluated the 6 trigonometric ratios, right? 1, 2, 3, 4, 5, and 6. The 6 of them. All right, so that is one way to evaluate the trigonometric functions for the special angles 30, 60, and 45 degrees, right? And again, depending on where you are on the equation, when you're rotating for an angle getting past the 90-degree angle, right? So you might want to use the trick for tracing a vertical line from the end point towards the horizontal axis, right? And then look at that angle form, right? And then see what the angle is. The other method is using the table, right? So we are going to have this table right here, right, to evaluate trigonometric functions, right? This table is in our textbook. Let me check on the textbook real quick, just for your reference. Where on the textbook is this? Let me see. This is table 2, page 804. All right. So that is where you can find that table. And I put colors here. I use Photoshop to make different colors, right? Our table is just it just has a white background, right? So to make it more colorful, easier to recall, I put these colors. And we can use this table, right, to find all sines and cosines. Sines and cosines are given for every single degree in what's this called, in radians, right? Let's list them all in degrees. Okay, when we list them all in degrees, this is 30 degrees, this is 45, this is 60, this is 90, this is okay, I think I'm gonna need help here. Hold on a second. I'm gonna need to look at the angle. Okay, so this is 120, and then 135, and then 150, and then 180, 210, 225, and 240, 270, 300, 315, and 330. And of course, 360, right? Let's not forget about the degree symbol, right? So if we go this route, guys, you don't have to memorize the triangles the same as we did on the previous approach. Personally, that's what I use. For some reason I memorize the triangles, right? And even if you don't know how, if you don't memorize, they're easy to deduce, right? By using Pythagorean theorem on the sides, right? It shouldn't be a big deal, right? But usually the tricky part is to find out where in the quadrant and how the signs change. All that is reflected here. For example, let me highlight some of them. For 5 pi over 6, 5 pi over 6, which is 150, we already did, right? Okay, I'm going to do it on the side. That's 150. Do you see how this is positive for cosine? I mean, positive for sine and negative for cosine. Do you see the signs right here? Positive and negative, right? And then let me do another one just to show you the relation so you can compare with the other one. The last one we did on this page was 11 pi over 6. Okay, 11 pi over 6. Let me highlight using green. 11 pi over 6. We get negative sine and positive cos. Okay, so let me do that. 11 pi over 6 is basically doing all this turn, right? From 0 all the way here. And see how the y value is negative and positive for x. In this case, sine is the negative, right? Because it's the opposite. And then this is positive because it's the adjacent, which is positive right here. Positive and negative. Let me grab another one. For example, the one we did up here on the previous page. 5 pi over 4. 5 pi over 4. Let me highlight using, I'm going to use blue. All right. Let me highlight those. And let me draw the corresponding picture, right? Which was around here. That was, right, that was, let me erase the curve only. Let me keep the triangle. And that's negative and negative. Do you see both sides are negatives? That is reflected here. See the relationship between them? All right. And we can use this we are going to use this table to evaluate all of them, all the 6 trigonometric functions, just the same way we did. Let's, as an example, let's evaluate the 6 trigonometric functions of, for the angle theta equals 2 pi over 3. Okay, so as a freebie, sine and cosine are given. Okay, so let's just copy the given values. Sine of 2 pi over 3, which I will highlight. Okay, let me highlight with purple. They're there. We don't have to do any calculation, at least for these two. Okay, at least for these two, we don't need to do anything. So sine, which is square root of 3 over 2, and negative 1/2 for cosine. All right. Now, it is our job now to calculate tangent using these formulas, right? So tangent is the same as saying sine over cosine, right? We are going to get into that on the next part of the video, right? On the following part. Actually, the last part when we cover what's this called? Trigonometric identities. Notice it's sine over cosine and cosine over sine, which is the reciprocal, right? That is cotangent. Notice how secant is the reciprocal of cosine and cosecant is the reciprocal of sine. By the way, I forgot the theta symbol for cosecant, right? You might want to write it down. Okay, so there should be a theta symbol here. Okay, so tangent tangent 2 pi over 3. This is sine 2 pi over 3 divided by cosine of 2 pi over 3, which are given on the table, and we have them here, right? So square root of 3 divided by 2 divided by negative 1/2. Okay, so you might just cross out these 2's, and negative root of 3 is tangent of 2 pi over 3. For secant, no, not secant not yet. Secant is rather cotangent. Cotangent theta, or 2 pi over 3 rather, is cosine over sine, or simply, well, cosine 2 pi over 3 over sine 2 pi over 3, which is negative 1/2 divided by root of 3 divided by 2, and you might want to just cross out these 2's, and we get as a final answer negative 1 over root of 3. And rationalizing this guy, and you might want to rationalize that guy, just multiply by root of 3 and divide by root of 3 to get negative root of 3 divided by 3. Okay. Secant, one more, secant. Secant 2 pi over 3 equals basically the reciprocal of cosine, right? So for the reciprocal of cosine, let me highlight it. If cosine is negative 1/2, its reciprocal would be negative 2 over 1, which is just negative 2. Okay. Last but not least, cosecant 2 pi over 3 equals the reciprocal of sine, but notice that sine equals square root of 3 over 2, so the reciprocal must be 2 over root of 3. Okay? And be sure to rationalize this denominator. Okay? That'll give us 2 root of 3 divided by 3. Okay? This tree is not looking good. Okay, right here. Okay, there we go. All right. Let's do another example. Okay, I believe the next example, yes, using the table 5 pi over 4. Okay, so the freebies are sine and cosine. And in a way, two freebies are going to be cosecant and secant. How come they're also freebies, if we will? Well, because on the one hand, cosecant is the reciprocal of sine, right? Okay, so let's look at the value of sine of 5 pi over 4, which we highlighted in blue. In this case, both sine and cosine are negative root of 2 over 2. Sorry about that. Okay, so negative root of 2 over 2, negative root of 2 over 2. So the reciprocal of sine, which is cosecant, is negative 2 divided by root of 2, and you might want to rationalize this guy, root of 2 over 2, root of 2. Okay, so this will be negative 2 root of 2 divided by the product between root of 2 and root of 2, which is 2. And you might want to divide this out and get a negative root of 2. Secant 5 pi over 4. So the secant function is the reciprocal of the cosine function. If cosine is negative root of 2 over 2, then the reciprocal for secant would be 2 divided by negative root of 2. And which is the same as cosecant. Do you notice that? And I'm not going to do the rationalizing. It's the same process. That's negative root of 2. Now the only one we're left to evaluate will be tangent 5 pi over 4, which by definition tangent is sine over cosine. Okay, so this will be negative root of 2 over 2 divided by negative root of 2 over 2. But we are essentially dividing the quantity by itself. That's going to give us a 1. Okay. And surprise, surprise, cotangent of 5 pi divided by 4, 5 pi over 4. Well, the cotangent function is the reciprocal of the tangent function, right? But what is the reciprocal of 1? Well, it's also 1, right? And there we go, our 6 trigonometric functions, all right? All right, so let's do the next topic. The next topic, evaluating trigonometric functions, method 3, using the unit circle. And you may have seen this before, maybe when you were in high school, maybe you took trigonometric from any chapter in trigonometry when you were in high school, right? So how do we read the unit circle? The unit circle, in a way, it's a combination of the triangles approach and the table approach. Actually, yes, it is indeed a combination. I'll show you why. Okay, first of all, let's look at what the unit circle is. Again, here we have a circle whose radius is 1, right? That means the radius right here is also 1. The radius right here is also 1, right, etc. That's also 1 everywhere from the center to any point, right? To every single point in the circle, the distance is 1, right? That's the definition of the circle, right? The definition is a set of all points whose distance, the set of all points that are equidistant from a fixed point called center, right? And that distance that is the same, the equidistance, right, is called the radius, right? So just to recall briefly about what the definition of the circle is, right? Now, what does that have to do with the angles and with the triangles? Well, of course, there's infinitely many points on the circle, if you will, right? However, there are special points, right? This first point right here, right? The one that form exactly a 30-degree angle, right? Do you see the connection with this and the triangles, right? And then let's look at this other point, the one I'm highlighting here. Do you see where am I going here? That's the 1 root of 2, right? And evaluating sine, that's root of 1 over root of 2, which rationalize gets root of 2 over 2, and same for cosine, root of 2 over 2. Okay, let me erase this. Let me look at other important points. How about this one right here? Right, this is the 60-degree angle, right? And draw a vertical line perpendicular to the x-axis, right? This will give us the 60, 90, 30, right? That is 1, 2, root of 3, right? And we can do the exact same thing for the rest of the angles, right? Remember when we evaluated the 150 degree, I believe it was 150. Let me go back and see my notes real quick. Yes, it was 150 degree. For the 150 degree, this is what we did. We went from the initial, right from the very beginning, and then we created another terminal line, right, all the way here. So the opening, the angle is 150 degrees, right? However, we were looking for the related triangle, right? Okay, drop a vertical line perpendicular to the x-axis and form the related triangle, right? The special triangle related to 150 degrees, which is, in this case, a 30, 60, and 90. Let me go back to that example we did. Okay, let me scroll up a little bit. Isn't that what we did? 150 degrees, right? We start at the beginning here at 0. We rotate this all the way to 150 degrees. However, what did we do? Do a vertical line and look only at a right triangle, which is this 30-degree angle, right? 30-degree angle. Same here. For the very last example we did, okay, let me erase this. I believe we did 330 degrees, 11 pi over 6, right? So, which is this point right here. Let me draw a triangle from here and do this as well, okay? So this is 330 degrees, right? All the way 330 degrees, right? However, these 330 degrees are 30 degrees away from the turn, right? From the next angle, which is 360. So this is 30, 60, and 90 degree angle, right? Okay, but what about this? What about all this 30, 60, 90? And what about this order pairs that we see around the unit circle? Okay, so in this case, all these points, okay, the unit circle is formed by all the labeled special order pairs. And they have the following form. Okay, so notice we have x's and y's, x and y, etc., etc., right? X comma y relates cosine and sine. All right, that is the x coordinate of all the x's, right? So let me highlight the x's. The x's, I'm gonna highlight with yellow. Let me highlight all the yellow ones, the x's only. Okay. Careful with the rotation here. I'm already getting dizzy here. All right. The x's are cosines, while I think I'm going to use blue for, no, not blue. It's not going to contrast very well. Maybe, no, green. let me do blue. What the hell? Okay. The y's, I'm gonna highlight them with blue. And the y values on the unit circle will be the sines. Okay. Now, how are we going to use the unit circle? It's going to be a combination, like I mentioned before, of the special triangles and the tables, right? Let's go back to the tables. The table gave us the sines here and the cosines here. Just the same way the unit circle is going to give us sines and cosines. The other four trigonometric functions, is our job to find them by knowing their definitions, right? Okay, let's evaluate the 6 trigonometric functions for theta equals 5 pi over 3. We're gonna do only one example, right? So sine of 5 pi over 3 and cosine of 5 pi over 3. So these two are basically they're freebies, right? Because they're given on the unit circle. All right. So let's see. Sine of 5 pi over 3. Okay, first of all, let's go to the unit circle and locate that 5 pi over 3, which is right here, the 300-degree angle, right? And we are going to use these two order pairs. This is going to be cosine, and the x will be cosine and the y will be sine. Okay, so cosine is 1/2 and sine is negative root of 3 over 2. Okay, in a way, the other freebies are cosecant, because cosecant is just the reciprocal, right? The reciprocal of sine. And I'm skipping the rationalizing process. You know how we did it on the previous pages, right? And then we're given cosine, therefore we can find secant by just finding its reciprocal, right? Which is just 2 over 1, because cosine is 1 over 2. Its reciprocal must be 2 over 1, which is just 2. Okay. It is our job now to find tangent 5 pi over 3 is the same as evaluating sine 5 pi over 3 divided by cosine 5 pi over 3. Okay? And in this case, we are given those values, negative root of 3 over 2 divided by 1/2. Notice how can we divide out the 2's, and that's going to give us negative root of 3. Okay? And again, in a way, when we get tangent, they're automatically giving us cotangent, because cotangent is the inverse or the reciprocal of tangent, right? So that's going to be 1 over negative root of 3, which is negative root of 3 over 3 after rationalizing this number. Okay, the same way we did it on the previous page. And that's one example on how we evaluated trigonometric functions of special angles, right? So how do you want to evaluate trigonometric functions? I will leave it up to you. Do you want to use triangles? Okay, be sure to put them in the correct quadrant every time you look at an angle. Having an idea of how the unit circle works gives you an idea of where and how to place the triangle in the corresponding quadrant, or use the table, or use the unit circle. You have three different approaches. Yes, we needed to spend a good minute on evaluating trigonometric functions just to show you at least three of the ways to evaluate these trigonometric functions. There's even more. If you put this topic on YouTube, you will find another way by using your fingers of the hand, right? I believe this is 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, and then they show you on YouTube a pattern for the order pairs 0, 1, 2, 3, and 3, 2, 1, 0 for sine and cosine. I don't remember the exact pattern, but I'm pretty sure you will find it on YouTube. Another way is by using pizzas actually um, uh, to find those related angles. Let me do the pizzas approach like real quick. I'm gonna do it on the side. Okay. So suppose we have 4 pizzas, right? And hopefully this comes out well, because when it comes to drawing this might be really hard. One pizza, another pizza. Well, actually, let me use shapes. I think it might be a good idea. Okay, and let me use this color. It's black and shapes. So I'm gonna do 1. Oh, come on. Okay. 1. Okay, control, copy, paste. And let me do another one here. So essentially we are going to compute, I mean not to compute, to consider 4 pizzas. Typically the pizza for kids, right? You go, I don't know, Peter Piper Pizza, Chuck E. Cheese, I don't know, they have these very tiny pizzas that are 4 slices each, right? Each slice is 90 degrees, right? 90 degrees, 90 degrees, right? So here are the points 0, 1, 0, 0, 1, negative 1, 0, and 0, negative 1, right? This is again cosine and sine. This is cosine, this is sine. This is cosine, this is sine, this is cosine, this is sine. Okay, so this is 90 degrees or pi over 2. This is pi, this is 3 pi over 2, and this is 2 pi, right? Or 0. Okay, let me go back to the table to confirm that cosine of 90 degrees is 0 and sine is 1. Okay, this is cosine and sine. Cosine is 0 and sine is 1. What about, let's look at the other ones. What about the other pizza? So this is, let's call this the personal pizza, right? And then we're going to have the small pizza. Okay, the small pizza will have typically 6 slices, right? 6 slices, and each slice is 60 degrees, right? No, wait a minute, 60, yeah, 60 degrees, 60, 60, 60, 60, 60, and 60, right? 60 times 6, isn't that 360 degrees? Okay, so what about it? Okay, how can we relate pizzas to triangles and trigonometric functions? So let's say we want to evaluate it. Okay, evaluate sine of 2 pi over 3. Okay, 2 pi over 3. Okay, that's pi over 3, right? That's pi over 2 in multiples, pi over 3 in multiples. Okay, these two right here, these two, it's telling us which slice are we in, okay? Starting at this at 0 right here, this is going to be the first slice, this is going to be the second slice, 2 pi over 3, and we're going to do a triangle there, right? And this is going to be 1 root of 3, actually -1 and 2. Okay, and then that's how you will get the triangle for it, right? Let me do another example using pizzas. What if we want to evaluate, let's see, 5 pi over 3. Okay, so what are we when we do 5 pi over 3? When we do 5 pi over 3, we are doing the first, second, third, the fourth, the fifth slice, right? The fifth slice. From there, we draw a triangle, right? This is going to be negative root of 3, 1, and 2. And then just use the same approach as in the triangles, right? Okay, let's do small pizza, medium pizza. Medium pizza, how many slices typically? Well, that's going to be 1, 2, divide that in 8 slices. Each slice will be 45 degrees. 45 degrees, multiply 45 times 6, that's going to give us, times 8, that's going to give us 360. Okay, so suppose we want to evaluate the trigonometric functions for 3 pi over 4. Okay, so this 3 right here is telling us, okay, 3 pi over 4, that's the third slice. So this is the first slice, the second slice, and the third slice. Draw a triangle right here. This is going to be -1. This is going to be 1 and root of 2, right? That's the multiples of 45 degrees or multiples of pi over 4, right? On the other hand, let's say we want to evaluate what about, okay, let me erase this real quick. What about 5 pi over 4? All right, 5 pi over 4. So for 5 pi over 4, they are essentially asking us to look for the first, second, third, fourth, and fifth slice, right? The fifth slice will be, this guy will give us the -1, root of 2, okay? That is the fifth slice. What if they want us to evaluate the trigonometric function for 7 pi over 4? Okay, so for 7 pi over 4, we go 1, 2, 3, 4, the fifth, the second, and the seventh slice, all right? Okay, and this is 1, -1, root of 2, okay? Same. Now, what about the other pizza? The other pizza would be the giant pizza or large pizza. How many slices is the large pizza or the giant pizza going to have? 12 in this case, right? And I'm going to do something similar to the 60 degree, but I'm going to divide each in 2. Okay, so what are we going to have? Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 slices. Each slice is 30 degrees, right? Each slice is 30-degree angle, right? So let's say they want us to evaluate the trigonometric functions to 5 pi over 6. Okay, as we did it on the previous examples, we are going to go 1, 2, 3, 4, 5. That's 5 slices, right? That's 5 slices, the fifth slice. And let's do the triangle related to that. That's the 30 degrees, so that's 1, negative root of 3, and 2. Okay, that is the fifth slice. Okay, let's say we want to evaluate the trigonometric functions for, I don't know, 11 pi over 6. We actually did, right? So we are going to go all the way to the 11th slice. So that was 1, 2, 3, 4, 5, 6. Okay, what about the 6th slice? The 6th slice would be 6 pi over 6. But isn't that the same as simply saying pi, right? Half of the pi, no pun intended, right? And the 6th, 7, 8, 9, 10, 11, right? And that is the triangle that gives rise to the root of 3, negative 1, and 2, right? Do you see? Hopefully you're able to see the relationship between the triangles, the unit circle, right? The related angles, right? And that's another approach, right? So actually, if you look on the internet, if you look every single book, every single book will cover the trigonometric functions in many different ways. The triangles, the unit circles, so tables, and I don't know. Again, Google it. Well, you can Google it up, or actually um, um, put it on YouTube. You will see a lot of ways to help you out and memorize. And again, do I want you to do in a particular way? No, you get to choose the way you want it to do, right? As long as you get the correct evaluation of the trigonometric function, I'm fine whatever you do, okay? Now let's move on to the next topic. The next topic is, let's see, periodicity of sine and cosine and negative angles. All right. Okay. So let's keep in mind, again, let's recall that an angle of 2 pi radians corresponds to one complete revolution, right? That is, okay, let me draw the picture for that, right? Let me draw a brief picture. And so we have the following. Okay, if I do this, this is what I'm going to obtain. Okay, I'm going to start here at 0 degrees. I'm going to do a whole turn. That's at 360 degrees or 2 pi, right? And I can even do another turn. That's 4 pi. And then another turn, which is 6 pi, etc., etc. Multiples of 2 pi, right? Now, okay, let me do a better picture. Oh, no, that's enough. That's good enough. Okay, so now, recall from the unit circle. Remember the points x, y that we got from the unit circle. So here we're going to use this a little bit. Okay, so those points, those important points on the unit circle are of the form cosine and sine, right? But we see that these values, right, these values of sine and cosine repeat themselves depending on the number of revolutions that they do, right? For example, let me go up here. So if okay, I'm going to start at 0, right? I'm going to start at 0 degrees, right? Or 0 radians, right? And then I'm going to do a turn to 7 pi over 4, all right? 7 pi over 4. But if I keep turning, I add 2 pi, right? What am I going to get? I think it's going to be 8 plus 7. That's going to be 7 pi over 4 plus 2 pi, right? Equals, so I think that's 8 plus 7, that's 15 pi over 4, right? But 15 pi over 4 is the same as saying 7 pi over 4 because it's exactly the same position, right? Which is also the same position if I said, I don't know, what is this? 15 plus 8, 23 pi over 4, right? So if I go from 15 and I do another turn, right? If I do another turn and I fall in the exact same point, that'll be 23 pi over 4, and so on and so forth. What I'm trying to say is, for example, if we were given to evaluate sine of 15 pi over 4, well, we don't have 15 pi over 4 in the unit circle. However, 15 pi over 4 is the same as saying 7 pi over 4, right? And then we are going to use the trigonometric values. Okay, let's look at some examples and let's look at the definition before looking at the example. So that means if we have sine of some angle plus 2 pi, right, plus 1 revolution, after 2 pi angles at any point we land exactly at the same value of theta, right? And same for cosine, right? Cosine function and sine function have the same rotation, right? Or not just 2 pi, but actually multiples of 2 pi, right? And so that means that sine and cosine are periodic, right? Periodic functions that repeat themselves after 2 pi, right? In this case, n, the n we have here is just an integer, right? 2 pi, and then 4 pi, etc., right? Okay, we're going to play with this in a minute. Now let's look at negative angles, right? Sine and cosine, where every time we want to evaluate sine of a negative angle, we get negative sign. We can, in other words, just pull out the negative sign and put it outside. All right. Okay. Now, what about cosine of a negative angle? When we have cosine of a negative angle, we can just make that negative sign disappear. Okay, how can we explain this? Okay, let me draw a little picture here. All right. And let me write a positive angle, right? Positive angle, theta, doesn't matter what that is. And this is one point right here, x, y, which corresponds to a point cosine and sine, all right? Okay, let me cosine theta, sine theta. Do you see the sign of the x value? Isn't it the x value positive, right? As well, I mean, that was the y value. The x value is actually this, positive and positive, right? Positive and positive. So no big deal for positive, for cosine and sine being positive when we have a positive angle, right? But what if we have this point right here, which is, again, the exact same thing as what we had. However, one thing that is going to change here, do you see the sign? The sign of x is positive, right? So that's why cosine is positive. And the sign of y is going to be negative. So that's why cosine of a negative angle, right, is still positive, while sine of a negative angle, it's negative now, right? So that explains that. Another way to explain this is to think about even and odd functions, but I don't think you went over even and odd functions when you guys took Math 96, but maybe you took it in high school, but that's a whole nother approach. Let's keep it simple for now and just use the point approach. Okay, so let's evaluate each of the following. Let's evaluate sine of 7 pi over 2. So sine of 7 pi over 2. Okay, notice that unit circle doesn't include a 7 pi over 2. In fact, that 7 pi over 2 goes past 360 degrees, right? So this is what are we going to do. So the idea is to rewrite this as some, I'm going to rewrite this 7 pi. I'm going to break it up in a way that I get a 2 pi. Okay, so there's many ways I can break up this 7 pi. Maybe 2 pi plus 5 pi, right? That's one way. And then divide by 2. But 2 pi divided by 2 is not going to give me a 2 pi. I need to break this up in a way that I get a 2 pi as one of my terms. So this is what I'm going to do. I'm going to break this up as 4 pi plus 3 pi. All right? Divide that by 2. And then when we split up this fraction, 4 pi divided by 2, 3 pi divided by 2, this will be sine of 2 pi plus 3 pi over 2. Okay? Notice this 7 pi over 2 is the same as saying 2 pi over 2 plus 3 pi over 2. What is the purpose of doing this? The purpose of doing this is to use this periodicity fact right here. Evaluating sine of certain angle plus 2 pi is just the same as evaluating sine of the angle, right? In this case, this is theta, right? Sine 3 pi over 2. Okay, and let's use the unit circle to evaluate 3 pi over 2. Okay, let's go up. 3 pi over 2, sine is negative 1. Okay, negative 1 is the final answer. Okay, let's do another example. Cosine of 5 pi. Okay, this one might require more than one step. Okay, so the way I'm going to break this up, okay, I need to have a 2 pi somewhere. Okay, so cosine of 2 pi plus what? That is 3 pi. Okay, but evaluating cosine of 5 pi is the same as cosine. When we have this 2 pi right here, disappears by periodicity 3 pi, and it just remains at 3 pi. And likewise, cosine of 3 pi is the same as cosine of 2 pi plus pi, right? Because of this 2 pi again, this is cosine of pi. Okay, let me go up to the unit circle. Okay, the unit circle tells us that cosine of pi, cosine, which is the x-coordinate, is negative 1 as well. All right. Okay, negative sine of negative 5 pi over 2. So first of all, you might want to take care of the negative sign. Keep in mind that when we have sine of a negative angle, we can just pull out the negative sign, right? That is negative sine of 5 pi over 2. Okay. Now, this is negative sine of 2 pi plus what number equals 5 pi over 2 in this case? This is pi over 2. And if you do 2 times 2, that's 4 plus 1 is 5, right? That's another way to decompose the number. Okay. And well, because we have a trigonometric function of 2 pi plus some angle, let's get rid of the 2 pi and just keep the angle, negative sine of pi pi over 2. But what is sine of pi over 2? Let's use the unit circle or the table, right? We'll use the unit circle. Pi over 2 is right here. Sine is the y-coordinate. In this case is 1. However, this is 1 with the negative sign being carried from the property we used before. Okay, now let's see. Cosine of 11 pi over 4, of negative 11 pi over 4. Again, keep in mind the negative sign first, right? However, when it comes to cosine, for cosine of a negative angle, we don't just put the negative sign outside as we did for the sine function. The cosine of a negative angle is the same as cosine of the positive angle, right? Cosine of a negative, it's the same as positive. All right, so now we need to break this up. So cosine of 2 pi plus what number equals 11 pi over 4? Okay, so there must be a 4 here, pi, right? So 2 times 4, that's 8. 8 plus what equals 11? 3. Okay, so this is cosine of 3 pi over 4. Okay, again, this, if you will, disappears, right? Because it's falling in the same place, right? So cosine of 3 pi over 4. Let's go to 3 pi over 4 on the unit circle. 3 pi over 4, and cosine is the x value, that is negative root of 2 over 2. Okay. All right. Now, let's move on to the next and last topic for this section, trigonometric identity. This one is going to take a good minute. We are going to work with, well, a little bit, not really solving equations, but rather proving and verifying trigonometric identities, right? So what are trigonometric identities? Okay, so there are like equations, right? Equations that hold true for every value of some angle and whatever domain they hold, of course, right? So some that we already saw when we were evaluating trigonometric functions, we already saw that cosecant is the inverse of sine, and just the same way we can say sine is the reciprocal of cosecant, right? Okay, on the other hand, we already saw that secant is the inverse of cosine. So we could say that cosine, its reciprocal, is secant. We also saw that cotangent is the reciprocal of tangent. So tangent is then the reciprocal of cotangent, right? Now, what about these trigonometric identities? I didn't list them, right? But for example, let me write down one. Let me write down, for example, sine theta equals 1 over cosine theta. What if I square both sides? If I square one side, we can square the other side as well, right? So that'll be sine squared theta equals 1 over cosine squared, not cosecant, actually, not cosine. Bear with me here. It's cosecant, rather. So cosecant squared theta, right? Or the same if I say it's sine to the 7th power theta, 1 over cosecant to the 7th power of theta, right? It holds for every single power of each, right? As long as you do it on one side, do it on the other side as well. Quotient identities, right? So the first group was called the group of the reciprocal identities. So the quotient identities, the ones that we already looked at, actually, this is tangent equals sine over cosine, right? So cotangent is the reciprocal, right? Sine over cosine, its reciprocal is cosine over sine. And the most important ones that we need to keep in mind, right? The Pythagorean identities. The Pythagorean identities, right? Because they come from the Pythagorean theorem, if you will, right? The fact that from the unit circle, right? This is x squared plus y squared equals 1, right? Those points on the unit circle, right? That's in fact the equation of the circular radius 1. Okay, but one thing to keep in mind is that we need to be able to play with these trigonometric identities. Actually, two more identities can be derived from this one, two more from this one, and two more from this one. I'm going to show you how to play with these identities first, okay? So let's see. Sine squared plus cosine squared equals 1. Okay, I'm going to subtract sine on the one hand minus sine to obtain this trigonometric identity. Cosine squared theta equals 1 minus sine squared theta. On the other hand, I'm going to subtract cosine squared to obtain a new identity. That'll be sine squared, okay, equals 1 minus cosine squared theta. We need to be comfortable with this, with playing with identities, because when we go over the examples, we may not be using the straightforward identities. We need to be careful about looking at the form that we were getting as we go. Okay, so what is the process of verifying trig identities? Okay, let me do an example first of all, right? Okay, verify the following identities. To verify the following identities, typically we are going to be given a complicated side, the left hand side. Okay, work on the left hand side. I will abbreviate it and make it look like the right hand side. That's the whole spirit of the problem in this case, right? Playing with trigonometric identities and go from one side and make it look like the other, right? Okay, so what are we going to do here? Okay, number one. By the way, there's many ways to verify trigonometric identities. For example, you might want to use one trig, you might want to use another trig one way or another. You should get, as long as you use the correct identities and you don't make up your own rules, you should get the same final answer, right? The same conclusion, which is to arrive to the right hand side. Okay, what about letter A? Notice this common factor of sine theta, right? That's the greatest common factor, and I'm going to factor sine theta. So sine theta times cosine squared theta minus 1, right? That equals a negative sine cubed theta. Okay, Notice this cosine squared theta minus 1, right? That looks kind of familiar. It looks familiar from what we did here, right? The thing is, I don't have, I have a cosine minus 1, not a 1 minus cosine. We can fix that, right? I'm going to do that too. I'm going to factor out a negative sign. And I will reverse the order of these two guys. 1 minus cosine squared theta equals negative sine cubed theta. Okay? Okay. What are we going to do? This guy is the same as saying sine squared theta from the definition, right? From this identity right here. If we move this plus cosine squared to that side, we are going to get sine squared equals 1 minus cosine squared, right? So I'm going to replace this whole quantity right here with sine squared. Okay, so we're going to have negative sine theta times, I'm going to use the same color just so you can see where is everything coming from, sine squared theta. Okay, let me erase this one to avoid repetitions, and I'm going to indicate it with an arrow only. Okay, and that equals negative sine cubed theta. Now we need to multiply this sine with that sine. Sine times sine squared. By using the laws of exponents, we are going to have a negative sine cubed of theta, and that equals, now the two sides are equal, right? And that's what we do. What did we do? Do algebraic techniques, substitute, change identities, right? In a way that we can get one side, make it look exactly like the other side. All right. So let's do another example. Okay. All right. Sine theta cotangent plus cotangent times cosine equals cosecant. Okay. What are we going to do here? Okay, so typically when you have sines and cosines and something else, a good strategy is to write cotangent in terms of sines and cosines. If we use our trigonometric identities, cotangent is cosine over sine, so you might want to replace the quantity cotangent with cosine over sine. Let's begin with that. So sine theta plus cosine theta divided by sine theta equals cosecant theta. Okay, we don't do anything on the right hand side, we just keep writing it. Oh, by the way, it looks like I forgot cosine here. All right, what are we going to do? First of all, multiply cosine with cosine, right, to get cosine squared theta, all right? Cosine squared theta divided by sine theta. And this plus sine theta, okay? And then equal cosecant theta. All right, you might want to think of this sine theta over here as sine theta over 1, right? Now, what is our goal? We want to combine these two fractions together. We have two rational expressions. Well, these are not rational because it's not polynomial over polynomial. Well, we have two fractions. Let's just call them fractions. So we need to have the same denominator in order to be able to be combined, right? To have these two fractions combined. So that's multiply by sine theta, divide by sine theta. Okay, and what are we going to get? Sine times sine, we get sine squared theta divided by sine theta. plus cosine squared theta divided by sine squared. By sine theta. That, just keep writing the right-hand side, cosecant theta. Okay, notice at this point, we have the same denominator, so we are able now to combine these fractions together. Okay, I'm going to continue over here. I'm going to write a big fraction, okay? And I'm going to do the indicated operation, sine squared plus cosine squared, right? Sine squared plus cosine squared divided by sine. Okay, that equals to cosecant theta. All right, it looks like that this is more complicated than the original, right? However, observe this expression right here, sine squared plus cosine squared. What is that equal to? Let's go up here and identify that Pythagorean identity. Sine squared plus cosine squared equals 1. So you might want to replace this with this whole thing is equivalent to 1. All right? So this will be 1 divided by sine theta. That equals cosecant theta. And well, what do we know about 1 over sine? Isn't that the reciprocal property, the reciprocal identity? 1 over sine is the same as cosecant theta, which matches now the right-hand side. And that's the end of the verification, right? All right, so let's do another one. Okay, let's look at another one, letter C. So for letter C, we have a couple of fractions, right? We wish we had the same denominator, right? But notice we have different denominators, right? One of the denominators is 1 plus cosine, and the other denominator is sine. So the LCD will be by multiplying both, right? So I'm going to leave some space here. 1 plus cosine theta equals that under sine. I'm going to leave a space for missing factors. Okay, that equals cosecant theta. Okay, so this whole expression, this huge expression, should be equivalent to cosecant theta. That's our main goal, to prove that, to verify that. All right, so let's add missing factors. Okay, let's multiply by sine, divide by sine. And over here, let's multiply by 1 plus cosine, divide by 1 plus cosine. Okay, so let's multiply this together. Sine times sine, this is sine squared, divided by 1 plus cosine theta sine. You might want to put parentheses around this guy. And then plus cosine times 1 plus cosine, that is cosine theta times 1 plus cosine theta. That is divided by sine theta, 1 plus cosine theta. Okay, that still equals cosecant theta. Okay, now notice the following. Notice that we have the same denominators, right? We may now combine these two fractions together. Okay, so do the operations implied sine squared plus this product right here, sine squared theta plus cosine of cosine theta times 1 plus cosine theta. Then divide that by sine theta, 1 plus cosine theta. and that equals to cosecant theta. Okay, now our goal is to focus on the denominator of the left-hand side. Let's do some simplifications. You will see how a lot of things are going to happen. It's going to look very interesting. So let me move on to that side of the page right here. Okay, and this will be, okay, what are we going to do? We are going to distribute the cosine over the two terms inside of the parentheses. This is sine squared theta plus cosine theta plus cosine times cosine. That's going to give us cosine squared theta. The whole thing divided by, this is going to be sine theta times 1 plus cosine theta. Okay. That should be equals to cosecant theta. Okay, how can we identify, what can we do about this, and how can we simplify this? Okay, one thing you might want to observe here, this quantity squared and this quantity squared. Does that remind you of anything? Remember that same identity we used earlier in the previous example? Okay. Okay, I'm not going to cancel anything. I'm not going to replace anything. The only thing I'm going to do, I'm just going to put these two together. The sine squared theta plus cosine squared theta plus cosine theta. Okay, then divide that by sine theta times 1 plus cosine theta equals cosecant theta. Okay. Now, the reason why we put this together is because sine squared plus cosine squared equals 1. So I'm going to replace that with 1 plus cosine theta divided by sine theta times 1 plus cosine theta equals cosecant theta. Now, observe this. This 1 plus cosine theta, you might want to think as having parentheses, and this guy, boom, boom, cancels. And what are we going to get? 1 over sine theta equals cosecant theta. But again, isn't that the same thing we did on the previous example? Right? 1 over sine, it's the same as cosecant theta, which proves or verifies the other side of the identity, right? See how this puts together a lot of things, right? So, okay, let me explain the bigger picture of this. So what have we done so far? Number one, define what angles are, right? Number one, define what angles are. Number two, look at the two different ways to express angles, degrees and radians, right? And then we move on to the next section in which we learn about the special triangles, the trigonometric ratios, right? What trigonometry is actually, and then define the sine, cosine, the tangent, etc. Right? That's the trigonometric functions, and then we learn to evaluate. So when we learn to evaluate these trigonometric functions, we're basically learning the arithmetics behind the trigonometry, right? Now what are we doing here? We are doing the algebra related to trigonometric functions, and just the same way you did LCDs and missing factors when you combined rational expressions back in your algebra class, we do exactly the same thing. However, we do a little extras to simplify trigonometric expressions. Now the question is, why do we do all this? Why do we spend a lot of time on trigonometric verifying trigonometric identities? And yes, we're going to spend a good minute because number one, The book, I don't think the book even does an example, or if it does, okay, let me check real quick. Does the book do an example at least? I think the textbook only does one silly example, and when you go to the actual exercises, it doesn't it doesn't give you enough tools to go about the examples, right? So that's why I'm going to do a bunch of these examples, and we are going to need to learn how to manipulate trigonometric expressions, because that will be needed a lot when we take derivatives and when we evaluate what's this called, integrals involving trigonometric, and we will do a lot of fun and play with those, right? So now let's see, let's do another example. So again, what I was trying to say, we're learning basically, by learning what angles are, we're learning the alphabet. For learning arithmetics, by learning the first part of this section, right, the trigonometric ratios and unit circle and all that, we're doing algebra, and soon we're going to do the calculus, right? Just the same way we were gradually going one step at a time. That's what we're doing now, but with trigonometry. Okay, so I'm going to write this 1 plus sine theta, okay, equals secant squared theta minus tangent theta secant theta. Okay, what are we going to do? Okay, okay, can we do 1 plus sine theta to the -1? I mean, it means the same. However, that's not going to be useful at all, right? That is not useful. So we are going to try something else. Okay, what are we going to try? The trick is called multiply and divide by the trigonometric conjugate. Conjugate, where have you heard that before? You might remember working with complex numbers. Remember, like 3 plus 4i, right? The conjugate is 3 minus 4i, right? Or when you have just a simple polynomial, right? Well, I mean a binomial, x plus y, its conjugate is x minus y, right? In fact, the product of conjugate binomials, it's a difference of squares, right? Let's combine that vocabulary with trigonometric identities. Okay, so the trick is to multiply and divide by the trigonometric conjugate. Okay, if we have 1 plus sine theta, we are going to multiply by the conjugate. The conjugate of 1 plus sine theta is 1 minus sine theta. Okay, now let's multiply this across. 1 times 1 minus sine, it's going to give us 1 minus sine theta, divided by the product of these two, 1 plus sine theta, 1 minus sine theta. Okay, that equals to secant squared theta minus tangent theta secant theta. Okay, that's what we're going to get. Now, observe the following. Observe the pattern here, a plus b, a minus b. Isn't that the factor form of a difference of squares? That is the same as saying a squared minus b squared, right? So I'm going to square the number 1. That will be 1 squared, which is just 1, minus sine times sine, that's sine squared. Okay. other side, the right hand side remains the same. Okay. Okay, what are we going to do next? Okay. Observe this 1 minus sine squared theta. Let me go back, right? Let me go back up here. Cosine squared is the same as 1 minus sine, or sine squared equals 1 minus cos. We're going to use one of those that gets derived from the original Pythagorean identity. Okay, so 1 minus sine squared is the same as cosine squared theta. The right hand side remains the same. Okay. Now, what are we going to do from here? Keep in mind the property of fractions when you have a plus or minus b divided by c. This is the same as a over c minus b over c. In other words, split it up. 1 over cosine squared theta minus sine theta divided by cosine squared theta equals secant squared theta minus tangent theta secant theta. Okay, I'm going to continue over here, up here. Okay, what am I going to do with these terms? Okay, number one. Okay, I'm going to keep the first term the same, the 1 over cosine. Well, why not? Suppose we didn't have the square right here. This is 1 over cosine. 1 over cosine is the same as secant. But because it's square, so this is secant squared. So there we go. We already get the first term, right? Okay. Now, I'm going to break up this cosine squared, right? This cosine squared right here, I'm going to break it up as cosine theta times itself, cosine theta, right? Because cosine squared is the same as cosine times itself, right? Now, and that still equals to secant squared theta minus tangent theta secant theta. All right. Now, I'm going to break this up a little bit further. This term I just circled, this second term on the left-hand side. So this is what got there. First remains the same. And I'm going to say minus sine over cosine times 1 over sine. No, not 1 over sine, 1 over cosine theta. Okay. All right. We are going to use a couple of identities here. What do we know about, first of all, what do we know about sine theta over cosine theta? And what do we know about 1 over cosine? The one I highlighted in green, which is sine over cosine, that equals to tangent theta. And 1 over cosine is the same as secant theta. And just keep carrying this secant squared. And surprise, surprise, isn't that the same thing as on the left-hand side? Secant squared theta minus tangent theta secant theta. And that's how we verify this identity. Okay, that's how. Again, see all the tricks we use, all the algebra tricks we use. This time we use a little bit of factoring, right? A difference of squares, right? Well, rather backwards, right? And reciprocals as well. Okay. Now let's look at letter E. Letter E, what about it? All right, let me look at this and organize this thing. Okay. Before looking at letter E, let me take a side trip. All right. I will show you a trick to memorize, or no, not to memorize, rather to derive all the Pythagorean identities, okay? So everything starts with sine squared theta plus cosine squared theta equals 1, right? That's where everything starts at, okay? I'm going to, just to avoid writing too much, I'm going to abbreviate this. I'm going to call s squared plus cosine squared equals 1, okay? That's s for sine and c for cos. I'm going to write this twice, okay? Sine squared plus cosine squared equals 1. Okay, the goal, what is the goal? I'm giving you like a, not a trick, I mean a way to derive, having a starting point, the sine squared and cosine squared, to derive these two formulas from them, okay? Let's see. Let's do the trick. Okay, the first, well, trick, if you will, divide everything by sine squared and divide everything by cosine squared on the second case. Okay? What are we going to have here? Sine squared over sine squared, aren't they going to cancel to give us a 1? And then cosine squared over sine squared. What is cosine over sine? Isn't that cotangent? Isn't that cotangent? So, and what is 1 over sine squared? Isn't that cosecant squared? All right. On the other hand, we're going to have sine over cosine, but sine over cosine is tangent. But both terms are square, so this is square as well. And then cosine over cosine, cosine over itself cancels out. And that's going to give us a plus 1 equals 1 over cosine. But what is 1 over cosine? Isn't that the same as secant? But this is squared, right? Because of this square right here. All right. That's how we can derive the other two identities from the sine squared plus cosine squared. And now the trick is we need to be comfortable to play with these new two identities, right? So on the one hand, this gives rise to two identities. Number one, cotangent squared equals cosecant squared minus 1, and what was the other one? Cotangent, and I think that's about it, right? I think that's about it. I don't think we need anything else here. Yeah, that's about it. No need to use second one. And over here, this gives rise to, let's say, tangent squared equals secant squared theta minus 1. So we give rise to two new identities. Now, how are we going to use these new identities here? Okay, so I'm going to highlight the secant squared theta. So secant squared theta is the same as saying tangent squared plus 1, right? I'm going to replace the secant squared quantity with the corresponding identity, which is tangent squared plus 1. All right? So tangent squared theta plus 1, and then minus 1. Bring this minus 1 from here, right? And then that's divided by secant squared theta equals sine squared theta. Right, notice how this 1 minus 1 cancels, and we are going to get tangent squared theta divided by secant squared theta. All right, and that's what we get. Now, how are we going to simplify this a bit further? I'm going to move this. Well, first of all, this is the same as saying tangent squared theta. Because this secant square is in the denominator, this is the same as saying 1 over secant squared theta, which equals sine squared theta but this secant squared, I'm going to rewrite it as its reciprocal. What is the reciprocal of secant again? The reciprocal of secant is cosine squared. Now, what remains to be done here is to rewrite this tangent squared theta as one of the ratio identities. In this case, tangent squared is the same as sine squared divided by cosine squared. And see what's going to happen here? That times cosine squared. And in this case, this cosine divides out, this cosine squared divides out this cosine squared, that is sine squared theta equals sine squared theta. And that's how we verify this identity. Okay. Let's do another one. Let's do a few more. We're almost there. We're almost there. Okay. So let's see. What about this one? We have fractions again, and the denominators, oh, they're not the same. Okay. One is 1 minus sine, one is 1 plus sine. Okay. So we need to find the LCD, put missing factors. So what do? 1 divided by 1 minus sine theta. I'm going to leave a space for missing factors, 1 plus sine. I'm going to multiply the first one by 1 plus sine divided by 1 plus sine. And on the other hand, 1 minus sine and divide by 1 minus sine. Okay, so that's what we're going to do. Okay, notice we can multiply these two together first. So that's going to be 1 plus sine theta divided by the product of these two guys right here, the blue and the orange, which is 1 minus sine times 1 plus sine. Okay, and then on the second term, we're going to multiply the blue with the green. That's 1 plus sine times 1 minus sine, or we can write it down in the, well, let's write it in this order. And 1 times 1 minus sine is 1 minus sine. That whole thing equals to 2 secant squared theta. Okay. Notice now we have the same denominator on both fractions. Okay. We are good to go and combine these fractions together. So we draw a big bar, 1 minus sine theta times 1 plus sine theta, and we do the corresponding operation in the numerator, 1 plus sine theta plus 1 minus sine. Okay, what are we going to get from here? 1 plus sine plus 1 minus sine. Okay, and this will be 2 secant squared theta. Okay, notice how this sine theta minus sine theta cancel each other, and we can combine this 1 plus 1 to give us a 2, right? Let me move on here to this side of the paper. Okay, this side of the screen. This will be 2 divided by, okay, I'm going to do another change as well. Do you see this form again? A minus b times a plus b. This is the same as the factor form of the difference of squares, right? So this is going to be 1 minus 1 minus sine squared equals 2 secant squared theta. Okay, now I'm going to replace this 1 minus sine squared with the Pythagorean identity. 1 minus sine squared is the same as saying cosine squared theta. Now, this is basically 1 over cosine squared, right? But 1 over cosine is the same as saying secant. Okay, and this is the end of the verification of the identity. Not cosine. 2 secant squared equals 2 secant squared. And that's the end. Okay. Letter G. Okay, letter G, let's do letter G. Okay, so our goal is to turn tangent cotangent into secant, tangent plus cotangent into secant times cosecant. Okay, what's going to be the trick here? Okay, the trick here will be to write down tangent as sine over cosine. I'm going to leave a space here. You'll see why. And then we're going to write cotangent as cosine over sine. All right. That equals secant theta and times cosecant theta. Okay. Oops, by the way, I need space here. Okay, there we go. That's enough. Okay. Now, we need to multiply by the LCD. Okay, the LCD is going to be the product of sine and cosine. Multiply by sine. And multiply by cosine. Okay, and now we can multiply this together times sine times sine. That's sine squared divided by sine cosine plus cosine times cosine. That's going to be cosine squared theta divided by sine times cosine equals secant cosecant. Okay, we're almost there. Notice now how we can combine these two together because we have the exact same quantity in the denominator. So write a big fraction, sine theta cosine theta, right? And that's going to be sine squared plus cosine squared. Where have we all seen this? Sine squared theta plus cosine squared theta equals secant theta cosecant theta. Okay, you might want to replace this with 1 because that's sine squared plus cosine squared, that's equals to 1. Let's go over here. And this is 1 divided by sine theta cosine theta, and that equals secant cosecant. Okay, this 1 over sine theta times cosine theta is the same as saying 1 over sine times 1 over cosine. I mean, maybe you can do the final step right away, right? But ultimately what we're doing is break it up into two different factors to write their corresponding identity, all right? And what is 1 over sine? Isn't that cosecant? And 1 over cosine is secant, which is the same as secant cosecant, right? Of course, they're just written in the reverse order, but it's the same. It's like 3 times 4, 4 times 3. That should give you the same answer, right? Okay. Oh my God, my hand is getting numb already. Well, we're one more page, and 4 short examples. Well, maybe not that short. One of them. Well, let's move on. All right, cosine theta times 1, cosine theta divided by 1 minus sine equals secant plus tangent. All right. Again, when you have only one term and you have a 1 minus sine to the first power, right, or cosine to the first power, again, conjugate. Conjugate will come into play here, all right? So the conjugate. So cosine theta divided by 1 minus sine theta, that equals secant, secant theta plus tangent theta, all right? Now, I'm going to multiply by 1 plus sine theta, which in this case it's the conjugate, all right? And we are going to get the following. Cosine theta times 1 plus sine theta divided by the product of these conjugate binomials in trigonometric expressions, right? 1 minus sine, 1 plus sine. That equals secant tangent. All right. Again, keep in mind this form, a minus b, a plus b. We have done it a couple times already, a few times. This is like the third, I think we do. Okay, so this is going to be, okay, in the numerator, I'm going to distribute the cosine. And I'm going to get cosine theta plus sine theta cosine theta divided by 1 minus 1 minus sine square theta equals secant theta plus tangent theta. Okay, let me continue over here. I'm running out of space. All right. So what are we going to have? We are going to replace the quantity in the denominator, this 1 minus sine squared, with cosine squared. that should be equal to the sum of secant theta plus tangent theta. So we are going to split this into two fractions, one cosine theta divided by cosine square theta plus sine theta cosine theta divided by cosine squared theta. Okay, so what is going to happen here? Well, this doesn't look like a theta. Let me write it down correctly. Secant theta plus tangent theta. Okay, and here we can divide out this cosine with 1 power of cosine in the denominator, leaving us with 1 over cosine, plus we can divide out this cosine right here with 1 power of cosine in the denominator, leaving us with sine theta divided by cosine theta. Secant theta plus tangent theta. Now, we know identities for 1 over cos, right? 1 over cos is secant, and sine over cosine is tangent. And surprise, that's the exact same thing as in the right-hand side of the equation right here of the identity, and this is verified. That's the end of it. Okay. All right, what about letter I? Okay, letter I, we're almost there. Almost there. So, okay, so sine to the 4 minus cos to the 4 is the same as sine squared minus cosine squared. So we're basically reducing the powers. How come? Okay, you might want to think of this as a difference of squares in disguise, right? Yes, even though it's not a square on the left-hand side, it's a fourth, but it's a square in disguise. What do I mean by that? So, what quantity squared equals sine squared? What quantity squared equals cosine squared? Okay, the first quantity, sine theta squared, because 2 times 2 gives us 4. And same for cosine squared, because 2 times 2 gives us 4. So we are going to write this as a difference of squares in which sine square theta plus cosine square theta times sine squared theta minus cosine squared theta. That equals forgot to write it down here. That equals sine squared theta minus cosine squared theta. Okay, but what do we know about the first factor? Sine squared plus cosine squared, isn't that equals to 1? 1 times sine squared theta minus cosine squared theta equals sine squared theta minus cosine squared theta. Okay, but what is 1 times whatever quantity? 1 times whatever quantity is whatever quantity, sine squared theta minus cosine squared theta equals the whatever we have on the right hand side, which is the same, sine squared theta minus cosine squared theta. And that nails it here. Okay. All right, more often than not, when we do integration, right, and also maybe derivatives as well, we are going to have combinations of logarithmic expressions with trigonometric expressions. So we are going to turn this ln of cosecant into negative ln of sine. Okay, how are we going to do that? Okay, so number one, replace this cosecant with 1 over sine theta. Now, you might want to recall one of the properties of logarithms, right? The one that says ln of a divided by b. It's ln of a minus ln of b, okay? That's the property you might want to recall to break this up into two different logarithms. One is ln of 1 minus ln of absolute value. I forgot to mention the absolute value. It's ln of absolute value of sine theta equals negative ln of sine, absolute value of sine theta. All right, but what do we know about ln of 1? Logarithm of the number 1, whatever the power goes to 0, and this is negative ln of sine equals itself a negative ln of sine, of absolute value of sine. Okay, that's another one. And the grand finale for this section. All right, so one more with logarithmic expressions. Okay, now what are we going to do here? Notice the sum here. Notice the addition sum. You might want to recall the property of logarithms in which the sum of two logarithms, ln of a plus ln of b, equals ln of the product ab. You might want to recall that part. Okay, now we are going to turn this ln of absolute value of cosecant theta plus ln of absolute value of tangent theta as ln of cosecant theta times tangent theta equals ln of secant theta, actually the absolute value. Okay, let's rewrite this cosecant factor into ln of 1 over cosecant times tangent, which is sine. Oh, wait, no, not 1 over cosecant, it's actually 1 over sine times sine theta over cosine theta, right? And that should be equal to ln of secant of absolute value of secant theta. Okay, at this point you might want to spot this part. Sines go away, all right? And we end up with the following. Ln of 1 over cosine equals ln of secant absolute value of secant. Okay, we have another identity here, 1 over cosine. 1 over cosine is the same as secant. Ln of absolute value of secant theta equals ln of absolute value of secant theta. And boom, boom, that nailed. And guys, this is the end of this section. Yes, this section was a bit long, right? And because I needed to slow down in this section because this is the fundamental part of what we need in order to understand the derivatives and the integrals, even though I'm going to do very basic, I'm going to go very basic about the calculus part because this is only Math 122, not the 150 course, which goes way deeper than what we're doing actually. So we need to have a very, very strong understanding about what the trigonometric ratios are, how to manipulate trigonometric identities, which is what we did on the last few pages, and of course how to find the trigonometric. And again, like I mentioned before, you're good to use the way that best works for you to get those trigonometric values, right? The values of trigonometric functions, that is unit circle, triangles, or the table, right? Okay, so, or the pizzas. Remember I showed you the pizzas. I took a time and showed you that. So again, so that's about this video. See you on the next video, which is finally 12.3 on calculus of trigonometric functions. So see you next time. Bye-bye.